In this presentation, I'm going to look at amines part 2. This is the reaction of amines, and it's the second part of your core notes for A2 to the organic section. Now, the reactions of amines fall into two categories. One is the fact that amines, because they've got the lone pair of electrons, they can react with H plus ions and they can add them on. And that would indicate basic behavior, the type of behavior we've seen before with Bronsted acids and bases. The other ability of that lone pair of electrons is then to add on to electron deficient carbons, that is ones with a delta plus, and in that case it's acting as a nucleophile. So you see that amines also can act as nucleophiles. Now, as far as the basic nature is concerned, in water amines have an alkaline pH, and this is due to the reaction with water. Now, in the first part of your core notes, we showed briefly the idea that that NH2 has got lone pair of electrons and therefore can take an H plus off the water. And what that'll leave is an OH minus, an excess of OH minus in solution, and that would be an alkaline solution. You are expected to show the Bronsted acid-base behavior of this, so if you want to pause and then try and assign Bronsted acid-base and then the conjugate acid-base pairs to those, you could do so. So looking at the nature of these, to get the Bronsted acid-base, this is going to be a Bronsted base because it's going to accept the H plus ion of the water, so it's accepting the H plus ion. This is donated, so it's a Bronsted acid. Then if you look at the reverse reaction, that would be the conjugate acid because that's what's going to lose the H plus, and that's going to be the conjugate base. And then to indicate your acid-base pairs, remember show the linking arrow there, so the Bronsted base, and that's its conjugate acid, and then the Bronsted acid and its conjugate base. The reaction of these with acids, again, depends on that basic nature. So the general reaction is acid plus base gives you salt. Now, we don't always get water with this. Sometimes you think of that general equation, acid plus base gives salt plus water. But quite often we get the salt just. So in this case, there's our amine reacting with something like hydrochloric acid. The H plus goes on to the amine group, becomes NH3 plus, and then the negative ion sits against that, the Cl minus. Now, the naming of these salts, we base it on this. So if that had been NH4 plus Cl minus, that would have been ammonium chloride. So it's a bit like ammonium chloride, but with an alkyl group attached, in this case an ethyl group, so ethyl ammonium chloride. With dibasic acids or diprotic acids like sulfuric acid, you would need two of the amines, so methylamine would react with two methylamines would react with one sulfuric acid, and then the formula of it would be CH3 NH3 plus, so each molecule would have an extra plus on there, an extra H plus on to it, and then two of those would sit against the sulfate ion, SO4 minus. So again, NH4 SO4 would be ammonium sulfate, and that's a little bit like that, but with a methyl group, so methyl ammonium sulfate. You could try the reaction of propylamine with nitric acid. Again, if you pause and then try it. So there would be the equation there, so propyl group with NH2 and nitric acid, and then that would give us the salt like this. Now, again, for the naming of it, if it had just been that, it would have been ammonium nitrate. It's got a propyl bit added onto it, so that would be propyl ammonium nitrate. Now, to reverse these reactions, if you, for example, had this, you had the salt, and you wanted to go back to the amine, one way of doing that would be to reverse this, to get rid of the H plus. And to get rid of an H plus of a group, you would use some sort of alkali, so something like sodium hydroxide, potassium hydroxide, something like that. So this ethyl ammonium nitrate reacting with sodium hydroxide, and basically what will happen is the H plus will go on to the OH minus, give us water. That leaves our two ions, Na plus and NO3, so that would give us sodium nitrate. So our products would be the amine back again, so the propylamine or 1-aminopropane, water, and sodium nitrate. So you could try again if you put the methyl ammonium sulfate formula down and try its reaction with sodium hydroxide for yourself. So there would be the formula of the methyl ammonium sulfate. This time we would need 2 sodium hydroxide because again we've got that dibasic acid, and then the product is going to be 2 of the amine, methylamine, water, and sodium sulfate. Okay, now these bases or the basic nature of amines is dependent on its ability to use its lone pair of electrons. So the more a lone pair of electrons is available, the stronger a base is going to be. And there is actually a scale of strength of bases. Now, a couple of things to look at in terms of the bullet points. We'll go over the bullet points here. So the strength of the base due to the ability of the amine to form a dative covalent bond between the nitrogen and its H plus ion, so the lone pair of electrons on the nitrogen. Ammonia only has hydrogen atoms surrounding it, and hence the lone pair of electrons are readily available. So you can see we put ammonia there in the middle. It's a reasonably strong base. Aliphatic amines, that's amines with alkyl groups attached to it. The alkyl group has a positive inductive effect. So the idea is that what it does is it pushes its pair of electrons away from the alkyl group. So if you looked at that alkyl group, there they are, that pair of electrons would be pushed slightly towards the nitrogen. Now what that's going to do is it's going to repel the lone pair of electrons. So the lone pair of electrons on this is going to be more available than, for example, in ammonia, where you've only got hydrogens that don't have this positive inductive effect. So if you look going up the scale of strength, where the strongest are over to the left, a primary amine with one alkyl group, well, you have one group of repelling that lone pair of electrons, so this lone pair will be more available in ammonia. But a secondary will be more available again. 2 alkyl groups are pushing the lone pair of electrons, so that lone pair is going to be even more available. And then the most available ones would be the tertiary amines, where you've got 3 alkyl groups pushing away. Going down the other end, weakness, you'll see these are the aromatic ones. Now remember, the aromatic amines have a delocalized pi ring of electrons. And because of the shape of it, that pair of electrons can get drawn into that delocalized ring. So instead of that lone pair being readily available, it's actually going to be spread around the ring. Now, you don't have to see the details of it if you go to further study. You look at how it moves around the ring and so on. But you don't have to see the details of this at this stage. Just accept that that pair of electrons gets involved with this, and it makes it less available. So compared to ammonia, this lone pair is going to be less available, and therefore would be a weaker base. If you put 2 benzene rings on, it would be even more drawn in, because you have 2 rings for that to be drawn over. And then if you had 3 rings, it would be even more drawn away as well. So that's going to be the weakest bases. Now, don't be worrying about learning those, just see why. And then these ones, asking about these 2 here particularly, would only be application questions at A level. So let's look at the reactions. So that idea of the lone pair acting as a nucleophile, where it would add on to things. And one example of the reaction, now we don't have to do the mechanism of it, but would be the reaction with ethanoyl chloride. Now when we looked at acyl chlorides in A2-1, we saw that acyl chlorides and amines could link together. And here's our structures. So there's our acyl chloride, so ethanoyl chloride, 2 carbons, double bond O, and then that carbon's going to be delta plus because the oxygen's delta minus. That chlorine is a good leaving group, and therefore it can come off and it forms the hydrogen chloride over here. And it'll react in a mechanism, I say, that we don't need to worry about. And the hydrogen from this NH2 group is lost, so one of the products is hydrogen chloride, and then these 2 link together. Now you'll notice that that linkage is a little bit like the amino acid linkage in proteins, C double bond O NH. And we'll see that this forms what's called an amide link. It's an amide group we've got there. So if you look at the molecule, that bit there, so going around there, you've got NH, C double bond O, CH3. You remember that's a little bit like our amide. So that is based on 2 carbons, ethane. This C double bond O NH, if that had been another hydrogen there, that would simply be ethanamide. So to name this, we base it on the fact that this is ethanamide. And then on the nitrogen of ethanamide, we've got an ethyl group. So therefore the name becomes N-ethyl. So on the nitrogen there's an ethyl group, and then ethanamide. So N-ethyl, so on the nitrogen there's an ethyl group, and then that molecule is ethanamide. So, do you want to try drawing the structures here? So propylamine with ethanoyl chloride and then 2-methyl-butylamine with ethanoyl chloride. So draw the structure, then see if you can try and apply that principle. So do you remember what we said? Look at the structure, see where the amide is. So then it'll be based on the amide. And then on the nitrogen is an alkyl group. So name the alkyl group that's on the nitrogen of the amide. Okay, so if you've drawn the structure, propylamine should look like that, 3 carbons with NH2. Ethanoyl chloride should look like that, 2 carbons, C double bond O Cl. Those react, we'll lose the hydrogen from here, the chlorine there. So there should be our product molecule. And then don't forget to do the balanced equation. Hydrogen chloride would be the other product. So if we look at it, there's the amide, C double bond O NH with 2 carbons. So again, it's based in ethanamide, 2 carbons, so ethanamide. And then this bit is a propyl bit. So on the nitrogen is a propyl, N-propyl, and then ethanamide. This one, 2-methyl-butylamine. So there's our butylamine, 1, 2, 3, 4. On the second one is the methyl group. Then ethanoyl chloride again, that's the one that Sia really had put onto your syllabus, and is C double bond OCl. The nitrogen will lose its hydrogen, that'll lose its chlorine, so hydrogen chloride's given off. And then we have the structure, 1, 2, 3, 4 carbons, the methyl groups, that's just that structure there, redrawn again. So that's just that bit of the structure. Then NH2 over here has become NH, C double bond O, CH3. So again, it's based on ethanamide. We've got 2 carbons in the amide bit there. Now, this alkyl group, again, it's on the nitrogen, so we're going to start off with N. And then what we have is butyl, 4 carbons, but on the second carbon of it is a methyl. So N, 2-methyl, butyl, ethanamide. Okay, the other reactions of amines are to do with the aromatic one, and it's going to be one called phenylamine, and it's produced ultimately from nitrobenzene. So again, here's a link in with some of our previous work. So you remember from our aromatic work in A2-1, we had seen how benzene is formed. So very quick reminder there of benzene. Overall, it reacts with nitric acid to form nitrobenzene and water. That's made by reacting benzene with a nitrating mixture. That's concentrated sulfuric acid and concentrated nitric acid. The electrophile is formed from this equation. Remember, we asked you to commit that to memory. And basically, there is going to be our electrophile, the NO2+. Then the mechanism, the NO2+ approaches the delocalized pi ring. The pair of electrons from the pi ring forms a bond between the nitrogen and the carbon. So you'll see the arrow ending up about halfway between the carbon here and the nitrogen. Then we've got our intermediate structure with its positive charge. We now show the hydrogen that was always there, but the skeletal representation didn't have it. And then that pair of electrons goes back in and reforms the delocalized pi ring, leaving our nitrobenzene structure. And you remember that that H plus is regenerated because sulfuric acid is a catalyst. The HSO4 can add on to that H plus and then go back to sulfuric acid again. So to convert that into phenylamine, which is really a starting compound for many, many molecules in the chemistry and in the chemical industry. Now, to do that, we have to convert nitrobenzene to phenylamine. So again, we need it reduced. Now, lithyl would reduce it a bit too much. You'd actually get a further reduction of the benzene ring as well. So the reducing agent that we normally use is a new one to us. It's tin and concentrated hydrochloric acid. Now, again, we don't have to see the details of how it works. You can look it up and see exactly how it does. But for organic purposes, do you remember we can basically say it adds on hydrogen. So we represent our reducing agent as 6 and then square brackets H, 6 hydrogens being added on. And if you look at it, really where the reduction is that bit there. It's the NO2 getting converted to NH2. So reduction in two senses. It loses oxygen, but it's also gained 2 hydrogens. And then to balance it up, the 2 oxygens go into water, and then that's ultimately why we need the 6 H's to turn those into water. So the equation can be represented as shown there. So benzene ring with NO2 plus 6 H's giving us our phenylamine. So the NH2 with the benzene ring and 2H plus, and also you could represent that with the delocalized pi ring of electrons as well. So it just depends which source you use where that comes from. Because this has a lot of hydrochloric acid, concentrated hydrochloric acid, ultimately what happens is whenever this is formed, there's lots of HCl. So you remember that's an amine group. So going back to reactions of it, that NH2 group acts as a base and it will form the phenyl ammonium salt. So basically phenyl, C6H5, that's the benzene ring, and that looks a wee bit like ammonium chloride, so phenyl ammonium chloride. That would crystallize and probably isn't as available as the phenylamine in some methods of separation. So quite often the next step to release the phenylamine is to get rid of that H plus off it. And again, to do that we use sodium hydroxide. So it ties in perfectly with the reactions we've seen earlier. NH3 plus Cl minus plus sodium hydroxide, that would give us the phenylamine plus water plus sodium chloride. So there's the conversion of the nitrobenzene to phenylamine. Now, to test for those amines, remember that we've got that this was a weak. Do you remember we said earlier on that this is a benzene ring with an NH2, it's going to be a weak base, and we've got the aliphatic ones where we've got straight chain carbons. Now, the test between those two is to use what's called nitrous acid. Now, nitrous acid is HNO2, sometimes written as HONO to show its structure a wee bit more. There's an N with an OH group and an oxygen attached to it. Now, this tends to be an unstable substance. We couldn't keep a bottle of nitrous acid in the lab. So quite often whenever we want to use it, we make it in situ, in other words, just as we need it, by mixing together sodium nitrite, NaNO2, and hydrochloric acid. And that will make nitrous acid, HNO2, and sodium chloride. The reaction with aliphatic amines, so those straight chain ones, is that basically converts that NH2 group, and again by a mechanism we don't need to worry about, into an OH group. So watch out for that maybe in some organic questions where you're given the structure NH2 and then maybe an arrow off saying HNO2, and it changes that amine group into an alcohol group, an OH. But the thing that's given off here is this nitrogen. And if you were to do this at normal bench temperature or even with cooling it down under ice, this reaction happens very quickly. There's an intermediate, what's called diazonium salt, which we'll look at later on. It's formed, but it's given off very, very quickly. And then what's given off is this nitrogen. So you see quite a bit of fizzing. So what tells you that is an aliphatic amine is that it fizzes very quickly. So do it at cool temperatures and this would start to fizz. On the other hand, aromatic compounds, now because of the benzene ring, they can form an intermediate, what's called diazonium salt. And the diazonium salt looks like that. So you've got the benzene ring with two nitrogens attached by a triple bond. So a little bit like we had there, that N with a triple bond, a little bit like we had with nitriles, but there's two another nitrogen this time. And that's what's called a diazonium salt, two nitrogens, diazo. And these are reasonably stable intermediates when it comes to aromatic compounds. So when you put this in at a low temperature, say about 5 degrees centigrade, so cooling it nice, this forms, the nitrogen doesn't come off. If you warm it up slightly, what will happen is that amine group it'll basically break down. So instead of going to this intermediate, it goes right through to the OH. And what you get then is nitrogen given off. So to test between it, you can use this. So if you add sodium nitrite and hydrochloric acid, an aliphatic amine will instantly fizz. Colorless gas produced as nitrogen. There's not really a simple test for nitrogen as such, but you get that fizzing and a colorless gas given off. An aromatic amine, if you do it on ice, so keep below 5 degrees centigrade, no visible reaction. And then as soon as you warm it up, you'll see a fizzing. So you could compare the two, do the two of them at 5 degrees centigrade. The aliphatic amine would fizz and the aromatic amine wouldn't. So that can be a test between them. Now, why do we do that? That seems a simple test. Well, the reason that we do this is that these diazonium salts are actually very, very good at reacting and giving us useful compounds, particularly dyes. There's a video that I've given a link to, and I'll send a link along with this PowerPoint in this presentation to an experiment which shows it being formed. It takes about 3 or 4 minutes, so I'll not play it through with this, and you can look at it and see. So it'll be embedded into the PowerPoint, and I'll send you the link as well, just to make sure that you can see it. And it'll show you the preparation of the diazonium salt, and then its further reaction to make azo dyes. Now, what are those? Well, those azo dyes are formed by coupling reactions, and they're very, very useful things. You're probably wearing clothes that have got dyes on them, and those dyes quite often are azo dyes. So to do the reaction, what you do is you couple, and a coupling reaction is a reaction in which 2 benzene rings are linked together through this N group. So you can see that that looks a little bit like that diazonium salt we saw earlier in the notes. So for the reaction to take place, one of the reactions that they quite often show is with phenol. So to get the phenol to work, you add sodium hydroxide and make the sodium phenoxide. So that's the first one, you dissolve phenol and sodium hydroxide. And then the solution is cooled, and the diazonium solution is added. So you add this benzene diazonium salt. And when those two are mixed together, what happens is the 2 rings link. So you'll see there's the diazonium salt with the 2 nitrogens, there's the phenol one, and those 2 bits link together. Now that linkage there, N double bond N with 2 groups either side of it, that is what's known as an azo substance, right, or an azo dye. And that is quite a bright yellowy orange solid, and that can be used as a dye. So there's one example of an azo dye that's produced from that. You can also use phenol amines. So this is why it links in with this bit of the course. So you could turn your the phenol amine into the benzene diazonium salt, and then you add phenylamine. Again, you get that linkage. Now you see the way the linkage happens. There's the NH2 group. This part of the benzene ring would link on to the 2 nitrogens there. And again, you'll see that nitrogen to nitrogen double bond there between the 2, and that's an azo dye. And that is a yellow solid against dye commonly called aniline yellow, and again can be used for dyeing various substances. So these strongly coloured azo compounds are known as azo dyes. And if you pause and go back and look at the video, you'll see the actual preparation of that, and you'll get a little bit more explanation of the azo dye being formed. Now, why do we use azo dyes? Well, you've used one. So for example, whenever we were doing acid-base titrations, you remember we used methyl orange. Now, you don't have to learn the structure of methyl orange, but look, there's it there. And if you look at the structure fairly quickly, you'll see it's obviously quite big with 2 benzene rings and so on. But look at this part here, and that's what really shows you that the methyl orange is an azo dye. Now, why does it act as an indicator? Well, the colours of these azo substances can be explained in terms of their structure, in terms of electrons. And if you look at how things get different colours, when something is something like a pigment molecule, basically it sits at a relatively low energy state, so the ground state or the low state of it. And whenever light comes in, sometimes if the chemical nature of the substance is correct, it can absorb photons of light, and that light could correspond to, say, visible light. And if that happens, the photon's absorbed by one of the electrons, and that increases it up to a higher state. Now, what happens is that photon disappears. So the colour that disappears determines the colour that the dye appears. So the colour of light absorbed determines the colour of the compound. So for example, if red, green, blue and violet light is absorbed, the substance appears to be yellow or orange. And that's the case with some of those azo dyes we saw where the light went in. Most of these colours have been absorbed, and then the substance appears to be a yellowy orange colour. The last little bit is just a quick read over, just to show you the idea of methyl orange. And the idea of it is that basically because you've got methyl orange in 2 forms, remember it's red whenever it's an acidic solution, and then yellow whenever it's an alkaline solution. And the reason for that is that the structure change is caused by the H pluses. So in acidic solution there's an excess of H plus. It can go on to those nitrogens that were linking it in the azo dye, the nitrogen double bond. And because there was lone pair of electrons on that nitrogen, it can link on and give you N plus. Now this structure is such that it will absorb light, and mean that the light that passes through and that we can see is red. But whenever you take away that H+, so in an excess of alkali where OH- has removed that, you've only got the nitrogen to nitrogen double bond in the middle. Now that causes a change in the chemical structure. It means the light that's been absorbed is different, and then you get this, the light that passes through appears to be yellow, and that would be the other form of it.